In this last video of chapter 6, I would like to discuss about the second example regarding the plane stress problem. In this example, a rectangular steel plate of 10 mm thickness, as shown in figure below, is subjected to 100 kN per meter square linearly varying pressure and 10 kN point load. The plate has modulus of elasticity of 200 GPa and Poisson ratio of 0.3. By using CST element, determine the unknown displacement and the stresses at point P. So the first thing that we have to do is to determine the type of problem so that we know which formula that we have to use in order to compute the properties or the matrix D. So in this case, the keyword from the question is the 10 mm thickness. Therefore, the problem that we are trying to solve is a plane stress problem because we are dealing with a very thin structure. Then, by knowing the plane stress problem, then we can compute the value D11, D22 and so on by using the formula dedicated for plane stress as shown in this slide. The second step is to draw the free body diagram in order for us to determine the number of degrees of freedom later on. Supposedly, in this problem, there are 4 elements as shown, element 1, 2, 3 and 4 with 6 nodes, node 1, node 2, node 3, node 4, 5 and 6 nodes. Nevertheless, if we look carefully, this problem is actually a symmetrical problem. As we can see, the bottom part at node 1 and 4 is having the same boundary condition as the above part at node 3 and node 6. Besides that, the applied pressure along edge 1 to 3, in this case, is also symmetry with the maximum pressure acting at node 2, which is at the line of the symmetrical line. The point load applied in this problem is also at the middle at edge 25, which is at the line of the symmetry. Besides that, we also have to consider the dimension. If you look carefully, the dimension above the edge 25, we have 2 meter. At the bottom part is also 2 meter. In other words, it is similar or symmetry. Therefore, we can simplify our calculation by cut this structure into 2 sections or 2 body. Then we only require to solve 2 elements instead of 4 elements. So let's say in this case we cut somewhere in the middle and we take the bottom part, as we need to consider or we need to calculate the stress at point P later on. So let's take the bottom part of the structure for our further analysis. So here is the bottom part of the structure after we cut into 2. Once we cut, the boundary condition at the line edge that being cut, which is 25, will become a fixed roller boundary condition. The pressure is remain the same as it depends on the thickness as well as the element length. Therefore, the pressure is still 100 kN per meter square. But for the point load, as it's located or acting at the middle of the symmetrical line, we just need to consider only half of the value. So the point load now has become 5 kN, which is half from its original value. Next, we have to determine the boundary condition at each of the nodes. Node 1 is pin supported. Therefore, both U1 and V1 are 0. And node 2 is fixed roller, meaning that it can't move in Y direction, therefore V2 is 0, but it still can slide in X direction. Thus, U2 is unknown. The same boundary condition is also observed at node 5. Therefore, U5 is unknown and V5 is 0. While at node 4 is pin roller supported, meaning that it can't move in Y direction, therefore V4 is 0, but it still can slide in X direction, that show that U4 is unknown. So in this case, the number of degree of freedom is 3, which are U2, U4 and U5. All the displacement or the unknown degree of freedom is the displacement in X direction. Like in the previous video, the third step of our calculation is to determine the stiffness metric for each element. Let's start with element 1. The first thing, as we discussed, we have to determine the element connectivity. For this element, I connect it using nodes 1, 5, 2. Therefore, for node 1, 5, 2, it will be numbered with 1, 2, 3, meaning that at node 1, it will become coordinate for x1, y1. Node 5 will become coordinate x2, y2, and node 2 will become coordinate for x3, y3. The surface area can be calculated by using the formula half time base time height, which is equal to 2 meter square for this element. Then we have to use the global K matrix, and we have to arrange the column and rows according to the element connectivity. As we have decided the element connectivity is from 1, 5, 2, then our column or rows will start with U1, V1, followed by U5, V5, and lastly U2, V2. Next, in order to simplify our calculation, we can apply the boundary condition. As we know, in this case, U1, V1 is equal to 0, V5 equal to 0, and V2 also equal to 0. Therefore, after we eliminate those unwanted rows and columns, there are 4 terms left in this K matrix. To make our calculation easier, similarly in the previous video, we can name this term with A, B, C. Let's say the first term as A, the second term as B, and this term again B, as the K35 is equal to K53. And the last term here, we name it as C. Next, in order to determine the term ABC that we have identified from the K matrix, we have to refer back to the element connectivity diagram of element 1, as we need to refer the value of x1, y1, x2, y2, x3, y3, and so on. Besides that, we also have to refer back to our calculated properties D11, D22, and etc. as we need it in our calculation later on for A, B, and C. To start or to simplify our calculation, I really encourage you to calculate this term at the first place. This term is located at the outside of the K matrix, so do not forget about this term. So in this example, the value T over 4A for element 1 is equal to 1.25 times 10 power negative 3. Once we have all the information, we can start to calculate the terms A, B, and C. For example, for term A, in this case, this term has been calculated, D11 has been calculated, D33 has been calculated. The next thing that we have to do is to determine the value of Y31 and X13. Y31, if we refer to this figure, we can check that Y3 is 2 and Y1 is equal to 0. So Y31 meaning that Y3 minus Y1 equal to 2. So Y31 is equal to 2. While for X13, if we refer to this figure, X1 is equal to 0 and X3 is also equal to 0, meaning that X13 is equal to 0. Therefore, in our calculation, we can eliminate this term. And by using the value D11, we can solve for the terms A, which is equal to 1.05 times 10 power 9. By using the same method, we can apply for terms B and for C. Once we have obtained all the values of A, B, and C, we can write our reduced K matrix for element 1. Now, let's move to element 2. Similarly, we have to determine the element connectivity at the first place. For this element 2, I connected it by using node 1, 4, and 5, which is still follow the rules counterclockwise. Therefore, for node 1 is numbered with 1, node 2, node 4 with 2, and node 5 with 3. Thus, for this element, the coordinate of node 1 will be x1, y1, the coordinate for node 4 will be x2, y2, and coordinate node 5 will be x3, y3. And next, similarly, we have to calculate the surface area of element 2 by using the same method, which is half time base times the height of the triangle. In this element 2, the surface area is equal to 0.002 meters square. Next, we have to determine the K matrix. So by using the global K matrix, and we have to arrange the rows and column according to the element connectivity. So in this case, as we connected the element using node 1, 4, 5, therefore the arrangement of the columns and the row is start with U1, V1, U4, V4, and U5, V5. And then the next step is to apply the boundary condition in order to simplify our calculation later on. So in this case, we know that U1, V1, V4, and V5 are equal to 0. Thus, we can eliminate those columns that having 0 values. After we eliminating all those unwanted rows and columns, again in element 2, there are also 4 terms left that we have to solve in order to obtain the reduced K metric for element 2. And once again, we name it the terms left in this metric with A, B, and C. Do not forget the term T over 4A that located outside the K matrix in our calculation later on. Okay, in order to determine the terms A, B, C in element 2, again, we have to refer back to the element connectivity of element 2 in order to refer the value of x1, y1, x2, y2, and x3, y3 for element 2. We also need to refer again the calculated properties D11, D12, and etc., which is constant for both elements. Next, to start our calculation, again, we just need to calculate the term T over 4A at the first place in order to simplify our calculation later on. So in this case, the T over 4A is equal or similar with element 1, which is 1.25 times 10 power negative 3. And then we can start to calculate or to determine the value for term A. Again, the term T over 4A is already calculated, D11 and D33 is already calculated. The only things that we have to compute is the value of Y31 and X13. This value can be obtained by referring to the value of X1, Y1, X3, Y3 in this figure. So in this case, Y31 is equal to Y3, which is 2, minus Y1, which is 0, equal 2. So this term will become 2, and for X13, X1 is equal to 0, and X3 is equal to 2. So 0 minus 2 will equal to negative 2. And if we solve these equations and we obtain the terms A is equal to 1.435 times 10 power 9. With the same technique, we can use to determine the value for terms B and C. Once we have obtained the value for A, B, and C, again, we can write our K reduced metric for element 2, as shown in this slide. After we determine the reduced K matrix for element 1 and element 2, the next step is to assemble the reduced global stiffness metric for this problem. So by combining these two metrics, then we will obtain the reduced global stiffness metric for this problem, as shown in this slide. Before we can set our system linear equation, first we have to obtain the equivalent nodal forces. As in this problem, there is a linear varying pressure acting at this side at h between node 1 and node 5, with the minimum pressure acting at node 1 and the maximum pressure is acting at node 2. Besides that, we can notice that this pressure is already applied in the global direction. Therefore, we can determine the value of Tx1 and Ty1 by referring to node 1. So at node 1, as the minimum pressure is 0, therefore Tx1 is equal to 0, and there is no pressure in y direction, therefore Ty1 is also equal to 0. While for node 2, there is a maximum pressure applied in x direction, which is the value is 100 kilonewton per meter square. Therefore, Tx2 is equal to 100. And there is no pressure applied in y direction at node 2. Therefore, Ty2 is equal to 0. Once we have obtained all these four values, Next, we just need to substitute this value into this equation, which is the equivalent nodal forces for linear varying pressure case. So, by substitute the value Tx1, Tx2, Ty1 and Ty2 into this equation, we can obtain the equivalent nodal forces, which is the first term here is correspond to Fx1, the second term is for Fy1, followed by Fx2 and Fy2 as shown at this equation. Next, to make our calculation easier later on, it is better to list down the total forces that involved in this problem. So we can list down the forces that acting in this problem from node 1 until node 5. So from node 1 and node 2, we can take from the equivalent nodal forces, and for the other nodes, we can refer directly to the figure of our problem. So in this case, there is only one node, which is node 5, that has been applied with a point load with value 5 kN. So we just need to add that value into this matrix in order to obtain the global forces that acting to our system or our problem. Next, in order to complete the problem in this example, let's determine the unknown displacement as we already obtained the global equivalent forces as well as the global K matrix. So we just need to set up the system linear equation F equal to Ku as shown below. So just put the right force correspond to the unknown displacement, then we can solve the unknown as shown in this slide. The next question is to determine the stresses at point P. If we refer back to the question, point P is located in element 2. Therefore, the stresses at point P are equal to the stresses in element 2. As we discussed before, in CST elements, the stresses and strains are constant within the element. Next, just apply the formula for the stress, and the product dP we can solve by using the given formula as shown here. To simplify our calculation, we can apply the boundary condition, as we know that in element 2, the value U1 is equal to 0, V1 is equal to 0, V5 is equal to 0, as well as the V4 is equal to 0. So we can eliminate those 4 columns and only consider these 2 columns for U5 and U4 in our next calculations. So by referring this element connectivity for element 2, then we can refer the value for X1, Y1, X2, Y2 and so on for our next calculation that need in order to solve for product dP. So once we have solved the product dP, the next step, we just need to multiply the dP times with the displacement that we obtained in the previous calculation here. So by multiply these two matrices, then we can obtain the stresses at point P or the stresses for element 2 as shown here in this slide. That's all for chapter 6.